What's up, guys? Welcome back to another video. Today we're looking at metallic bonding. Okay, so it's a very little unit. We don't have to talk a lot about it, so let us get to it. In order to understand metallic bonding, I want you to take a look at this image that I've drawn out. Okay, so we have these positive metal ions. Examples such as magnesium that has a charge of Mg2+, as we see over here, and sodium that has a charge of Na+. All the elements in period 1 and in group 1 and group 2 are metals, okay? So they are also positive. So all of those have metallic bonding. So the other ones I want you to take a look at is these electrons. Not only are they electrons, they are delocalized electrons. That means they are kind of separated from these atoms. We know when ions are formed, there's positive formed and then there's negative formed. So these are the electrons that are separated from these atoms. Okay, let's say we have a magnesium atom. It's separated into two, which is the magnesium 2+, and the delocalized electron. Okay. Not only are the electrons delocalized, there are, if you can look at them, there are a lot of them, okay? So we call them a sea of delocalized electrons because there's a lot of it, all right? So if you're asked to describe what metallic bonding is, you want to talk about the electrostatic attraction. The electrostatic attraction between these positive ions, sorry, that's wrong, okay, the positive metal ions, as well as the sea of delocalized electrons, because there's always attraction between positive and negative, and in this case it's electrostatic attraction, okay? So between the positive metal ions as well as, let me use my highlighter, and the sea of delocalized electrons. Another thing you need to note is that this whole structure over here is a giant metallic lattice. Why is it lattice? Because we can see any metal, big or large, it's going to have a regular arrangement, okay? This, if it's going to continue, is going to look the same. So not only is it giant, and we know it's metallic, it's a lattice. That means it has a regular arrangement. So if you mention these 2 points right here, the first and the second one, you will be good to go when you're asked questions about describing a metallic bonding. Now, you want to look at the structure and bonding and relate it into why metals are good electrical conductors as well as good at malleability and ductility. Let's look at good electrical conductors, okay? This is the basics. You have, let's say, a metal fork and a plastic, what do I write here? Straw, okay? It's not visible. So a plastic straw. So what would you use to conduct electricity from one end to another in this case? So from the batteries to the bulb here, if you want your bulb to light up. So would you use your straw here or would you use your fork? Can't draw, sorry. So I would use my fork because it's a metal fork, because it's a good electric conductor. But why is that? If I go back to this image right here, we have a lot of negative ions, a lot of electrons just laying around. They are delocalized, and okay? So these sea of delocalized electrons, what they do is they carry charge. They kind of like, they are trucks, you know, like little trucks with wheels. Cannot draw a truck either. So they carry charge from one end, from here, they load it and they leave it here. Okay, so this is what these four metals do. So this is why they are also very good electronic conductors. We use them when making wires. Our wires are metallic. You know, the little wires, little colored things that we see are also metallic as well. So now let's look at malleability and ductility. So what does it mean that a metal is malleable? It means it can be hammered into thin sheets. And I have an example here for you. There's a big rock, gold rock here, or a nugget, and we've hammered it into a coin here. So it can be changed, it can be transformed. Whereas plastic, you can't really hammer, you know, it into something thin, can you? And when we look at ductility, is the ability of a metal to be, to be turned to wire. We use metals because they have properties such as malleability and ductility that are very essential in making these wires and making these thin sheets. So, what does it mean? Why are metals suitable for these properties? Now I want you to look at the structure yet again. We're going to go back to the structure all the time because that's how you can also understand the bonding here. These metal ions, okay, in terms of structure and bonding, you want to talk about the metals, the metal ions, the positive metal ions are, can slide over each other in layers, okay, without breaking bond. And because the electrons, we have a sea of electrons, can also adapt to the sliding and strengthen the bond. Bonds will not be broken. So therefore, whether you've made it into a thin sheet, whether you've crumbled it into the rock again, it's still going to have that bond. So it's not going to break apart. It's still going to be, the metal that it is, and it will not lose its properties. Okay, so that's all for today. It's very short, so thank you all for joining me. If you want to look back at the different types of bonding, you can look at the playlist. So see you in another video.